So talking about problem-solving methods. In this last equation here, M1V1 is equal to M2V2. That's from chapter 4. But you might have used this equation in Chem 4 to do what? To find the concentration of a titration problem or of a...
Doesn't it not work for certain things? It looks like you could use that equation, but you'll end up getting the wrong answer.
Yeah, right. In Chem 1A, you'd get the wrong answer. You could have used this in Chem 4. In fact, I think they have this equation in the Chem 4 lab manual for the titration problem there, but we are not going to use this equation for this titration. This equation is usually used for solution dilution. This is the solution dilution equation. And so normally when we come into lab, we'll read through the experiment and have an idea of what's going on. For this particular lab, we have to dilute some of our stock solution. Normally when we buy chemicals here in the laboratory, we try to buy as concentrated stuff as possible because it's cheaper. And then if we need a lower concentration, then we'll do the solution dilution. That is, we'll take the concentrated stuff and make some dilute stuff. It's like if you buy cleaner. You can buy the concentrated stuff and then dilute it yourself, or just buy the cleaner straight as is, or already diluted for you. You're going to save money with the concentrated stuff, and that's what we do in lab here. We save money. So rather than buying 0.1 molar, we're going to make 0.1 molar sodium hydroxide. How do we make 0.1 molar sodium hydroxide? Did anybody do the pre-lab? Did you? Okay. How many milliliters? So what we're going to do is this. We have a 6 molar sodium hydroxide. This is what we call our stock solution. This 6 molar sodium hydroxide stock solution was actually diluted from more concentrated hydrochloric acid. 6 molar sodium hydroxide is called dilute, and the more concentrated, we can buy pure sodium hydroxide. It's a solid salt, and so we could just take that salt, dissolve it in water. Sodium salts are soluble, and so this is one way. But we're going to take this 6 molar sodium hydroxide solution, and what we want is we want to make 0.1 molar sodium hydroxide solution. And so how do we do it? Well, we could take our entire 6 molar stock solution and dilute it to 0.1 molar, but we don't want to because we don't need that much. How much 0.1 molar sodium hydroxide do we need for this lab? We would need 500 milliliters. And so this would be like a pre-lab or quiz, type question that would be asked. And so the 6 molar sodium hydroxide stock solution is in the back there. It's in the reagent bottles that we have there. And so we need to make 500 milliliters of 0.1 molar. How are we going to do that? Well, if you see a bottle that says 6 molar, how many sig figs is this? 6 molar. 1. So our stock solution is not very precise. It's about 6 molar. And therefore, we're going to form about 0.1 molar. But we're going to use this equation. When we use this equation here, M1 is this. M2 is this, V2 is this. And so what's missing here is V1. We want to know how much of the 6 molar stock solution we need in order to make our 500 milliliters of 0.1 molar base solution. And so we're going to solve for V1. V1 is equal to M2 V2 over M1. What I like to do here is I like to have the ratio of molarities here, M2 over M1 like this, times V2. And this first fraction here, the ratio, this is called the dilution factor. So we have different dilution factors. It could be a 1 to 3 dilution or 1 to 2 dilution. If it's a 1 to 2 dilution, the dilution factor is 1/2. Let's see, something like that. But what is our dilution factor here? For us, the dilution factor is going to be, we want 0.1, and we're starting off with 6, and the volume we want is 500 milliliters. And so what this gives us is, can somebody calculate this? Well, we're only really allowed 1, but we want to be more precise, so we'll just go 8.33 milliliters of 6 molar sodium hydroxide. Rather than round it down to 8. Now 500 might be just enough, or it might be a lot, or it might be not enough. We don't want that situation where it's not enough. So this is why I'm writing a little bit more sig figs than I'm allowed, because I want to make sure I err on the high side. And so let me show you what we're going to do. Do you recognize this flask here? Yeah, what is it called? This is a Florence flask. And so what I'm going to do is I'm just going to measure. It doesn't have to be exact because this is only 1 sig fig anyway, but what we want to do is we want to make it as precisely as possible. And so I'm going to put in 8.3 milliliters of 6 molar sodium hydroxide into a 500 milliliter Florence flask. If I'm going to err, I'd rather overshoot. I'd rather make the sodium hydroxide more concentrated than less concentrated. You know, but not by too much, you know. And so, you know, 8.5 is fine, up to 9 is fine, you know. And then I'm going to pour it in here. And then I need to dilute it to a final volume of 500 milliliters. And so the way the solution dilution equation works is like this. And we're not making a very precise solution here. So we're going to pour in about 8.33 milliliters of 6 molar sodium hydroxide into a Florence flask. And then we're going to fill with water. Now, does a Florence flask tell you, if I fill it up to the top, do you think that's 500 milliliters? No. All the Florence flask is designed to do is hold at least 500 milliliters. And so they're going to make it bigger. And so what we're going to do is we're going to say the 500 milliliters is going to be around the neck here. And so what we're going to do is fill with water to about the neck. So we get our concentrated sodium hydroxide in here. Actually, bases we usually use blue, but I'm going to use that for the water. And then fill it to the neck. And so this is going to be approximately 500 milliliters of about 0.1 molar sodium hydroxide. This is all very qualitative. We're not being very exacting here. And the reason we're not being very exacting is because our stock solution, if our stock solution were 6.00 or 6.000, something more precise, then yeah, then we could be more precise here, but we can't. We only have one sig fig. And so there's a lot of uncertainty there. All right, so this is going to be our base solution. Our base solution is going to go into the big Florence flask. And then we're going to prepare our acid solution. So let me talk about the preparation of the acid solution. What acid are we using? For part 1.
Is it oxalic acid?
Yeah. We're going to use pure oxalic acid. But it's oxalic acid what? Dihydrate. Or oxalic acid dihydrate. And what's the formula for that? And this is a solid. And so we're going to have crystals of oxalic acid dihydrate. This is it right here, what it looks like. And now we're going to make our acid solution. Our acid solution, we have to do a calculation. Did anybody do the calculation for this? This is just a dimensional analysis calculation. And so we do the dimensional analysis calculation, and then we get the grams of oxalic acid. Oxalic acid, I'm going to abbreviate oxac.2H2O. Now, this is a stable hydrate. And what that means is it doesn't change. So for example, let's say it's a little bit more humid one day, a little bit less humid another day. And what happens with these waters of hydration is they wiggle themselves into the crystals. And so this crystal is going to consist of oxalic acid molecules packed together in the solid state, and then the waters wiggle their way in. And it turns out we can only get 2 waters per oxalic acid molecule. It's a 2-to-1 ratio. So for every oxalic acid molecule, 2 waters wiggle their way in. And so this is a stable hydrate here. So as long as the humidity in the room is okay. Let's say if we're out in the desert, it might not be so stable. Let's say the relative humidity was 0%. If the relative humidity is 0%, then that's going to dry out these crystals. But as long as there's some humidity, then this is it. All right, and we call this a primary standard. primary standards have to be stable and relatively pure and a solid, usually a solid. In other words, primary standard has to have what we call a reliable weighing form. Yeah, right, solid. So for example, measuring volume, is it very easy to do compared to measuring mass? What's easier? Mass. Let's say you're weighing 10 grams of solid on the balance. How many sig figs can you weigh that to? Well, 4 decimal places, and so 2 preceding the decimal and 4 after the decimal, that's 6 sig figs. So you can weigh things pretty accurately and quite precisely on a balance. Whereas with a burette, a burette, how many sig figs can we get from a burette? Well, 2 decimal places, which means 3 sig figs from 0 to 10. Let's say 9.xx, that's 3 sig figs. And then past 10, we could get 4 sig figs. And so we get 4 sig figs from volume. And so primary standard has to have a reliable weighing form because we can take weights with good accuracy and good precision. This sodium hydroxide stock solution here is not a primary standard. Oh yeah, thanks. My burette's leaking. Just dump that. Thanks. All right, so we're going to do this. This is called the preparation of a standard acid solution. From our primary standard, oxalic acid dihydrate. Okay, so this is a pre-lab, from pre-lab. But nobody's calculated it? No? So it's like 2.4, 2.5 grams. In this range. I forgot the exact number. We can calculate it, but we're not. This one you're going to err on the low side. So don't overdo it with oxalic acid. So there are different ways we can weigh the oxalic acid directly. One, we could bring a beaker in there and tare it, let's zero it, and then just tap in about 2.4 to 2.5 grams. Make that probably less than 2.4 grams. Go with that. Just around 2.4, 2.3 something. How about, that should be good. So tap in about 2.3 something. But we need to weigh it to how many sig figs? It's a primary standard, so we should weigh it to the max number of sig figs, which would be, well, it's only 2, so it's going to be 2 plus the 4 decimal places is going to give us 5. So we're going to weigh this to 5 sig figs. A little less than 2.4. And then we're not going to use a Florence flask. We're going to use one of these. This is called a volumetric flask. And this volumetric flask has been calibrated for 250. How many sig figs is 250? That's what it says here, 250. It's like 2 or 3 sig figs. But it's not. This is calibrated to 250.00. I don't know why they didn't write the .00 there, but it's 5 sig figs. And so, what's that?
I wonder at what line? Like 250.
At this line here.
This line I can't see it.
Yeah, it's etched into the glass, and so if you run your fingernail over it, you should be able to feel it. The etch mark is going to vary depending on,
Yeah.
you know,
And that's TC, right?
manufacturer. Yes, this is TC.
I wonder what picture.
It's marked here. This
Oh,
one
wow.
is 20 degrees C.
More precise.
Yeah, yeah. This is expensive. Those are expensive. All right, so that's option one. Option one, tap some into the beaker and then use some water to transfer all of it into your volumetric flask. You could tear this, but tapping it into the mouth of this is very difficult without spilling. And so we're not going to bother tearing this. So just tear this. Or alternatively, you could use a piece of weighing paper, although this, I don't know what would be better, the beaker or the weighing paper, because some people were using weighing paper and accidentally spilling some crystals off the weighing paper. But you can make weighing paper from just normal paper, or you can buy it. They actually sell weighing paper designed specifically for weighing objects. Weighing paper, weighing boats, all kinds of things. So I used to use plastic weighing boats for my chemicals. And so there are these disposable plastic boats that you use, tear, dump in your chemical, and then you can throw them away. This is the low budget one. We're going to just make some weighing paper boats by folding it in half and then folding it in half perpendicular. So you make a little dish. And then you can weigh it on this dish. Okay, so you transfer some of that, and then what you can do is you can try to tap this in here very carefully, try not to spill any crystals out of this. So this might not be as easy as this, the beaker. But whichever way, we need to get that. And so we know, what we need to know is how many grams of oxalic acid dihydrate primary standard I have here to as many sig figs as possible. And so we're going to get 5 sig figs. All right, so here we're going to get 2.xxxx grams of, I'm going to abbreviate oxalic acid dihydrate as oxax.2H2O or OXAX-D, OAD, oxalic acid dihydrate. And then we're going to put that into our 250 milliliter volumetric flask. Here. And so we'll get the crystals down here, and then we're going to add water, deionized water. So probably not all the crystals have dissolved. You can try to dissolve it in the beaker if you want, or we could try to dissolve it in here. Even if we get it all dissolved, what we want to do is we want to make sure everything's well mixed. And so I would fill it maybe not all the way to the line, because if you fill it all the way to the line, it's difficult to mix. And so I would recommend filling it a third to half full. And this way we can swirl it. It's much easier to swirl. There's another way that people mix it, and that is they stopper it and then invert it. So we have different stoppers. We have rubber stopper. We have glass stoppers. This is a ground glass joint here, so the glass stoppers fit in there very tightly. It provides a nice tight seal. And we have plastic stoppers. Plastic stoppers have a twist handle on it. So if you twist it to the right, it expands. If you twist it to the left, it contracts the circumference of this. And so if you use a rubber stopper, make sure you clean this with soap and water and rinse, dry it. Because today somebody had cleaned it just with deionized water, and when they inverted it like this to mix, some kind of brown contaminant came off the stopper and contaminated their oxalic acid solution. And so if you invert it a bunch of times like this is a good way of mixing as well, or swirl it like this. Okay, once it's well mixed, then we're going to fill it. We need to fill it so that the meniscus lies right on that line. And so what I'll do is I'll get the bulk of the water in there. And then I'll just add a little bit, drop by drop. You want to use the medicine dropper or the dropper to fill this to the line. Because what happens if you add too much water? Let's say I try to fill this to the line and then I accidentally overshoot the line. So I overshot the line. Can I take some out? No, I can't, because it's going to mix with oxalic acid molecules and it's already... So I can't take it out. Do you know what I have to do? I have to dump this and start over again, which is a pain because I got to dump this and then clean this with DI water. Fortunately, I don't have to dry it because I'm adding water anyway, but still, it's a bit of a pain. So be very careful. Don't overshoot the line because you only have one chance. And if you blow it, then you have to go back to square one. And so hopefully we'll get it right on the line. That is, the bottom of the meniscus matches that. If we did that, then this should be 250.0 milliliters of what was the molarity of the oxalic acid supposed to be? 0.08 molar? Yours is going to be different because you're not going to use the exact amount, right? We're going to use a little less. And so what we should say is 0.0 XXXX molar oxalic acid standard. And so this, let's just take a look at the pre-lab calculation. The pre-lab calculation was the number of grams of oxalic acid dihydrate required to make 0.08 molar (250 milliliters) actually to make 200. Let me add that in here. 250 milliliters of 0.08 molar oxac standard solution. All right, so what I'm going to do here is just use some dimensional analysis. This is a dimensional analysis problem. So 0.08, we're going to call this exact. Moles of oxalic acid per liter of solution. But this is an intensive property. I usually want to start off with an extensive property, and 250 milliliters would be that extensive property. So we're going to go with 250 milliliters. We're going to say all this is exact. And so in exactly 250, I want 0.08 molar. So I need to go from milliliters to liters. So sorry, I got to squeeze this in here. 1 liter is 1,000 milliliters. And so milliliters cancel. This is ox-ax solution. Liters cancel. And solutions cancel. That leaves me with moles of pure oxalic acid. But do I have pure oxalic acid or do I have oxalic acid dihydrate? I have dihydrate. And so what I have to realize is that for every oxalic acid molecule, and so for every 1 mole of oxalic acid molecules, which is H2C2O4, I need 1 mole of oxalic acid dihydrate, H2C2O4.2H2O. So what happens is when you dissolve it in water, you break apart the molecules of oxalic acid. When you break apart the molecules of oxalic acid, the water is free from the what we call the void spaces, or the interstitial sites, or the maze of passages between the molecules. So they're freed from there, and therefore we release the molecules from the waters of hydrate. Oh, I have this backwards though, because when I form my oxalic acid solution, it's just pure oxalic acid. And so this means that for every 1 mole of pure oxalic acid, H2C2O4, I need 1 mole of oxalic acid dihydrate, H2C2O4.2H2O. Okay, so that works there. And so moles of pure oxalic acid cancel, and that leaves me with moles of oxalic acid dihydrate. And what I'm after is grams. And so what I want to do here is I want to do a quick calculation of the molar mass of oxalic acid dihydrate. And so let's go ahead and do that. I have these memorized. Hydrogen's molar mass or atomic weight is what? 1.008 for elemental, H or H2. Or I use 1.01 in compounds. Well, 1.01 is leading to round-off error, but you're going to make a compromise. You know, a little bit of round-off error for speed compromise. And so sometimes it's worth the speed because calculations with 101 are easy. How about carbon? Do you have that one memorized? 12.01. Oxygen? 15.994, but I don't like that. For speed, I like 16.00 is not as accurate, but it's okay. We're going to compromise for speed. And therefore, I can calculate the molar mass of oxalic acid dihydrate quite quickly. So if I want oxalic acid dihydrate, how many hydrogens do I have total? Well, let me write the formula here again. H2C2O4.2H2O. So how many hydrogens do I have total? 6 hydrogens. And so speed, 606. It's an easy calculation. How many carbons? So 2402. How many oxygens? 6 oxygens. So the way I do 6 would be, there are different ways you could do it. You could do 2 oxygens would be 32. 32 times 3 would be 96. And so this comes out 8, 0, 10, 16, 126.08. So we go back over here, and we could do 126.08 grams of oxalic acid dihydrate per mole. Now we have to factor in the water, even though water is not part of the oxalic acid molecule, water is stuck in the oxalic acid crystals. Do these crystals look wet to you? No, but there's water stuck inside. There are 2 water molecules for every oxalic, and this is a stable hydrate. This is the dihydrate. We could dehydrate it by taking it out in the desert or heating it up. But it's good. And so let's see, was I right in 2.4 to 2.5? Since nobody did the calculation, somebody did the calculation this morning, so I just used their number. And their number was about 2.5. But I didn't check it. Let's check this. So 250 divided by 1,000 times 0.08 times 126.08. Yeah, they're right. 2.5216. How long do you think it would take to get it right on? Oops. 2.5216 grams of oxalic acid dihydrate. Do you think you could get it right on? No, I don't either. I don't even want to try. It would be a huge headache. So what I would do is I'd err on the low side. So I'd probably go under 2.5 grams. Because if you overshoot this, you know what happens? If you have too much acid, that requires too much base. But we have a limit. What's the limit of how much base we can dispense with this burette? Well, the top mark here is 0. The bottom mark here is 50. So this burette can dispense a maximum volume of 50 milliliters before you have to refill it. How many times do you want to have to refill it for one titration? I would say 0. I don't want to fill it. I mean, I want to keep it to a minimum, basically. And so fill it once, hopefully, and that's enough. The problem is that even this morning, some people got all the way down to 50, and it still hasn't turned pink. And so what that means is, if you get all the way down to 50 here and it still hasn't turned pink, what should you check first? Probably the first thing I check is, did you add the phenolphthalein? You're supposed to add how many drops of phenolphthalein?
Does that happen a lot?
It happens a lot, yeah. 1 or 2 drops of phenolphthalein. And then the other question is, do you add too much base? So your base is, no. If you added too much base, then then you don't have enough acid. If you added too much base, then we'd have the opposite problem. We'd be using too little. So if you only go down to 5 milliliters and it's already turning pink permanently, then that's too concentrated. But it would be either our acid is too concentrated or our base is too dilute. And so they're issues. And so anyway, what we're going to do is we're going to make this is a standard solution. You could think of it as a secondary standard. We're going to make this secondary standard from our primary standard. And the secondary standard, what we know about that is we know its composition to a high degree of accuracy and hopefully a high degree of hopefully a high degree of accuracy and precision. And so we should have at least 4 sig figs here. Actually, can we get more? This is wrong. How many sig figs should I get from this 250 milliliter volumetric flask? 5. I only had 4 here. And how many sig figs should I get from the balance? 5. And so that means my molarity here should be known to 5 sig figs. I only wrote 4. That's wrong. And so this is what we call a standard solution. A standard solution is going to have a fairly accurately and precise, fairly accurate and precise concentration. All right, so that's the preparation of the standard acid solution. And then what are we doing with the titrations? And so part 1, we're going to do the process of standardization. But we're going to standardize what solution? So the sodium hydroxide solution, how many sig figs do we know the sodium hydroxide solution to right now? Just 1 sig fig. We want to know the concentration of the sodium hydroxide solution to at least 4 sig figs. And in part 1 of this experiment, that's exactly what we're going to do. We're going to determine the concentration of the sodium hydroxide solution to 4 sig figs. This process is called standardization. So we took our primary standard and we made our secondary standard, the oxalic acid standard solution. Now we're going to take our oxalic acid standard solution and standardize the sodium hydroxide solution. And so we're going to do this here. I'm going to, first I'm going to clean out this pipette by rinsing it out with some water. But is this pipette easy to dry? No. So one thing you could do is you could try to squirt out the water, but even if you squirt out the water here, it doesn't all come out. There's going to be surface coating of water. And so what a lot of people do with normal glassware is they put it in the drying oven. That's what a major use of the drying oven. However, we do not want to use volumetric glassware in the drying oven. We don't want to dry it that way. And the reason is because as this heats up, the glass softens a little bit. If the glass softens, the shape changes. If the shape changes, it's no longer calibrated and you're going to have a systematic error. It's always going to be reading off. You know? And so we don't dry it that way. And there are other ways to dry it. If we can't use a drying oven, another way we could dry this is by washing out the water. There's water coating the inside of this. We can wash out the water using a solvent like acetone. And so we used to use a lot of acetone to dry glassware. The acetone would just wash out the water and evaporate, leaving the glassware dry. Water is quite soluble in acetone. But we can't do that anymore because we just dump the acetone down the sink. It's no longer allowed. It's 3 carbons. Acetone is propanone, they call it. Ethanol is okay, but ethanol is too expensive. So we could wash this out. Ethanol is great. 95% ethanol works great. 100% ethanol. 100% ethanol we call absolute ethanol. That works great too, but it's too expensive. And so what we're going to do is we're going to sacrifice some of our oxalic acid standard solution. And so I'm not going to put this in here. If I put this in here, I'm going to contaminate it with water, the rinse water. I don't want to contaminate it with the rinse water. So I'm going to transfer this to a beaker here, and then I'm going to sacrifice this for rinsing. I actually put too much in there. I don't really have to use all that much here. And so what I want to do is I just want to rinse off the inside walls like this. I can let some drain out this side, and rinse off, and let some drain off this side. So rinse it like 2 or 3 times, okay, and then you're good. Now this is wet with oxalic acid standard solution. So in theory, I can just go ahead and put this in here without contaminating it. But normally we don't like to. I used to pipette out like this all the time because it's just easy, quick. Normally you're supposed to use a transfer beaker, but I wouldn't use the transfer beaker that you did the rinse in because this is already contaminated, right? Or just do this. And so now we're going to pipette. When we pipette 25 milliliters, this 25 milliliter, although it says 25, it's good to 25.00. This is good to 4 sig figs. So when I put 25 milliliters in here, so, oops, that's not a good seal, it was leaking. But I'll get a seal, drop it to there, and then deliver it. So that will be 25.00. There will be a little bit left, like a drop or two left in the tip. Should I blow that out? No. Yeah, this is a TD pipette, not a TC. If it were a TC pipette, I'd blow it out. Okay, then we're going to put that into a 250 milliliter Erlenmeyer, which I don't have, but you have, right? Erlenmeyers are the best because it's difficult to splatter when you swirl this. If you were to swirl this in a beaker, it's easy to splatter out. But this you can swirl quite nicely. And then we're going to set up our burette. In Chem 4, you probably used two burettes. You used a blue burette and a red burette. This Chem 1A, we're only going to use one burette, the blue burette. And the blue burette's for the base. But we don't know who or what's in this, who put it in or what it is. And so what we're going to do is we're going to rinse this burette with water first. Just put in some in here. We have little funnels for the burettes too. You could use that, or you could use a beaker with a spout. And so I rinse off the inside walls of the burette, and then also the valve here, which we call the stopcock. You rinse that out too. And now this is wet with DI water. One way to tell if a burette's clean is if there are beads of water. If there are beads of water, it's dirty. If you see a lot of beads of water in here, then you should use soap and water to clean it. But I don't see too many beads. And even if you saw beads, don't clean it with soap and water because it takes too long. We're just going to rinse with DI water. All right, now this is contaminated with DI water. But my base, I'm just going to use tap. My base. I have 500 milliliters of about 0.1 molar. Do I care if it gets contaminated? I do care because I'm standardizing this solution. So I want to know the concentration of the sodium hydroxide in here to 4 sig figs. So what I'm going to do is I'm going to sacrifice some of my sodium hydroxide. So you're going to either use a transfer beaker, which I would probably do here, and transfer some sodium hydroxide for rinse. And so we'll rinse this off, same thing as the pipette, with our base solution. Okay, now this should be, rinse it like 2 or 3 times with a small portion. A small portion is called an aliquot.
I'm sorry, why don't we want to use water? Or that.
If you use water, then each time you refill this, you have to make sure you use the same amount of water that was in here. Otherwise, it's going to change the concentration a little bit with each trial. And so we got to make sure that the amount of sodium hydroxide in here and the amount of water stays the same ratio. If we have more or less water with each trial, then we're going to see fluctuations. Yeah. Okay. Now, after we rinse this 2 or 3 times with sodium hydroxide, I'm just going to pour this from this. This is very dangerous because it's easy to pour it out of the mouth. So use a funnel for this. But sometimes we take shortcuts for speed. Yes, that's just one more piece of glassware you have to clean. But then you got to worry about cross-contamination. All right, the first thing is we got to get rid of the air pocket here. And sometimes you could just let it drain and it gets rid of the air pocket. Sometimes there's an air bubble trapped in the valve here. If you're having trouble getting rid of the air pocket, then what I recommend is this. This is filled to here, but you can tilt this almost horizontal. Or maybe I could tilt this horizontal and it doesn't spill out the end here. I'd have to kind of get it inverted. Now it's starting to spill out there. But what you can do is if you're having trouble getting that air pocket out, then tilt it about horizontal, open it. I see a little bubble coming out of the valve here. And that little bubble is going to give you a headache. that's going to give you a lot more random error, because air is compressible, so it can squeeze down or it can expand out. If it squeezes down and expands out, you're not getting a good, precise reading of the volume. And so air is one of the major reasons why people get poor precision in titrations. And so I have an air pocket. I didn't see, there's no air pocket here, but when I tilt this down like this, now I see an air pocket. Do you see that? That air pocket right there came out of the valve. And it's easy to get out. This air pocket wants to stay in the valve here. It's easy to get out if you tilt it horizontal, because this is like trying to push a balloon or a basketball. Or if you try to take a volleyball or a basketball and push it to the bottom of the swimming pool, is it easy to do? No. And so that's what you're trying to do. You're trying to push this mini ball down to the bottom of the swimming pool. It's hard to do. But if you put it horizontal, it's easy, because we can just get it out. Just by a little bit of shaking there, and it's out. Now the valve has been cleared of the air pocket, and the tip has been cleared of the air pocket. And then I'm going to start, but now I'm too low. Do I need to start right on zero? No. Starting on zero could be considered bad technique or good technique. It could be considered good technique because that will give you the maximum volume, 0 to 50. It could be considered bad technique because it's just slow. Getting this on zero just takes too much time. So you might as well get it below zero and take a reading. You got to take a reading anyway, right? And so it depends. If you have lots of time and you don't mind wasting time, then get it right on zero. But anywhere close, but under it's fine. And so most people consider it bad technique to start on zero. So I'm below zero here, and I'm going to read the volume to how many decimal places? 2 decimal places. So I'll get my initial volume here. Now I'm ready for my titration. So I get my acid. I'm going to pipette 25.00 milliliters of acid in here. Then I'm going to add a drop or two of phenolphthalein. Not too much phenolphthalein, because phenolphthalein is also an acid and leads to a systematic error. And then I'm going to add some water. Is it okay to add water to this now? It turns out it's okay, because I'm going to know how many moles. So I know the molarity of this to 5 sig figs. I know the volume to 4 sig figs. So I can figure out the volume times the molarity gives us moles. I'll know how many moles of oxalic acid I have in here. So it doesn't matter if I add more water. If I add more water, it's not going to change the number of moles I'm titrating. And that's what we need to know. How many moles of oxalic acid am I titrating? The first titration is usually a throwaway titration for me, because I don't know how many milliliters, but I don't want to go drop by drop for too long. Because if you go drop by drop for too long, it's going to take way too long. So what I do is I don't even swirl it. I just go ahead and let it drain until I see pink. And then when I see pink, then I'll stop it and then swirl it. See if it persists. And so usually the first titration for me is throwaway, because I want to do it quick and get an idea of where it is. But still collect the data, because you might need that. Okay, or it might not be. If you're pretty good with this, then you'll get it close, and then you'll know I'm close. And then you want to go like drops, like drop, 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 or drop, wait, let's try to get one drop without a stream. Drop, But what we want to do is we want to get it to go from colorless to pink within, well, it has to stay pink for 30 seconds, but it has to go to colorless to pink that persists for 30 seconds within 1 drop, preferably less than 1 drop. Now, how do you get less than 1 drop into the flask? Well, one way you can get less than 1 drop into a flask is by this. Like a half a drop won't fall down. But what you can do is you can touch it to the inside of your flask, and that will get it to fall down. And then make sure you rinse off any splattered sodium hydroxide in, like that. We use this to rinse off the walls as well. And so to get a half a drop, you can suspend half a drop on the tip. Oops, that was too much. Stop, and then either tap it in or spray it in with a wash bottle. You don't want to be that sloppy, but you should be better. All right, and then once we have this, we'll know how many. Well, we'll look at the calculation later. What we want is we want good precision. So we're always using the same amount of acid. And so we're going to do a precision check. We're going to be using 25.00 milliliters of AC standard. And then in trial 1, we're going to get the volume of sodium hydroxide. The volume of sodium hydroxide is V final minus V initial. It's trial 1. Then we're going to go to trial 2, get the volume of sodium hydroxide. And then trial 3, get the volume of sodium hydroxide. They should be exactly the same. Do you think they're going to be exactly the same? No. Why? Probably due to random error, right?
What's the accepted percent error for this lab?
Less than 1% is good. But we're not going to calculate the percent error. What we're going to do for precision is we want the percent difference between the biggest V and smallest V. This is for the sodium hydroxide. To be less than 0.5%. So the percent difference here, this is equal to the biggest volume minus the smallest volume of the three. So just look at the three volumes, pick the biggest one, subtract the smallest one from it, divide by the smallest one, times 100%. And this gives us the percent difference. And this should be less than 0.5%. If it's greater than 0.5%, then you should do trial 4. If you do a trial 4, then pick the three closest. So throw one out, the furthest one. If you have to do a trial 5, then hesitate, because the sodium hydroxide has to last for part 1 and part 2. So if you use too much sodium hydroxide in part 1, you won't have enough for part 2. So it depends on how much each titration took, but if you have to move on to trial 5, then give it some thought before, because we might go on to part 2 instead, and then if we have leftover, come back to part 1. This is a 2-day lab, so if we don't finish part 1 today, it's not a big deal. We're going to continue next week. Okay, any questions on this? All right, if there are no questions, let me just finish off by saying the third method of solving problems is system of equations. And the most common system of equations that we're going to do is 2 unknowns and 2 equations, etc. If we're doing 2 unknowns and 2 equations, then I have an alternate method of solving these. But let me give you some examples. From chapter 1, an example would have been this. At what temperature in Fahrenheit will we get the same temperature in Celsius? That is, at what X temperature in Fahrenheit will we get the same temperature Y in Celsius? In other words, at what temperature does X equal Y? Do you know already what it is? Is there a temperature in Fahrenheit that it would be the same in Celsius? Yeah. So that would be an example of it. In chapter 2, there's one example with the, I think it was sodium chloride and magnesium chloride mixture. And so the 2 unknowns were, what is the percent sodium chloride And what is the percent magnesium chloride in the mixture? And so they gave us the total percent chloride in the mixture given Z percent chloride. In chapter 3, there are a number of them. I can't remember. It was either ethane and methane. Do you know the formula for methane? Do you know the formula for ethane? C2H6. If we have a mixture like this, it's the same thing. What is the percent methane? What is the percent ethane in this mixture? And it's going to form some CO2. That's how we're going to determine it, from how much CO2 formed. From how much CO2 formed from the combined combustion, we can figure it out. Or it might have been this. I can't remember if it was methane or methanol. What was the formula for methanol? CH3OH. And the formula for ethanol? CH3CH2OH. And the same thing here. We wanted to figure out the percent of each of these in a mixture from combusting the mixture to form CO2. Or it could be the one in the homework. The one in the homework is magnesium and aluminum mixture. And so it's the same thing here. How much of this mixture is magnesium? How much of this mixture is aluminum? From the amount of hydrogen gas that forms. So I have a different way. I assigned a tutorial problem for these types of system equation ones, but I have an alternate method you could use for the two equation, two unknown type problem. I'll talk about that tomorrow. All right, any questions? I'm going to stop here. Now, actually, maybe I'm not going to stop quite yet. What we're going to do is we're going to finish the last lab first. All we have to do for the last lab is we're going to get our crucibles from the oven and a desiccator. And we're going to put all the crucibles in the desiccator. You can't fit the beaker in there, it's too big. And we don't have enough crucibles for everyone, so you might have to share some. But you can fit probably 6 crucibles on the floor of a desiccator without too much difficulty. Or you might have to stack it. You're going to let those cool. It says to cool them for 10 minutes. I think 10 minutes is overkill. They'll probably cool down like in 5 minutes or less, 3 minutes. And then you're going to take them over to the balance. Now, you got to cool them in the desiccator so they don't rehydrate. And so we're going to quickly weigh those. And we don't want to handle those with our fingers either. We're going to handle those with a Chem wipe and then weigh those. Once you weigh them, then it's okay. You can handle them with your fingers. You can let them reabsorb the water. We just need to know the dry mass. That's all. And so what you're going to do is you're not going to clean those out. You're going to put those back in the original numbered beaker with the paint on there, the painted beaker. Put the crucibles in there, cover it with watch glass, the ribbed watch glass, and return it to the stock room. And then we're done with that experiment. We'll do the calculations later. You just need to collect the masses today. All right, any questions with that? Yeah. All right, that's it then for discussion.